Okay, let's move on to section 3.2. We're going to take a look at the continuous compounding, effective interest rate, and bond pricing. So we'll take a look at the continuous compounding first. So continuous compounding basically meaning it's compounding continuously. Later, I'm going to show you one of the real-world application of continuous compounding. Also, the effective interest rate is widely used in financial field, financial industry. Bond pricing is also one of the important financial instruments. We're going to take a look at that in detail. So first of all, let's review the compound interest formula, A of t. A of t here is what we call the ending balance, okay. And then equal to principal. P is principal amount. You can also say initial investment. We also have a N, which is N is number of compounding periods, and I is annual interest rate, and T is the time years. Okay. So the compound interest formula is principal times open parenthesis 1 plus R over N to the NT power. Now, we try to develop the equation determining continuous compounding. So continuous compounding indicates we have infinitely many compounding periods. Continuous compounding indicates infinite many compounding periods. Okay. So now let's assuming principal equal to $1 or 1 unit, rate is 100%, and then time t equal to 1 in 1 year. Okay, so let's fill in the table first. Okay, here yearly compounding yearly, so A equal 1. So one more time, P is 1, rate is 100%, and time t equal to 1. So here that should be equal to principal $1, 1 unit times 1 plus 100% 1 by raised to the n number of compounding period 1 times t times t is 1. Okay, so this is 1 plus 100% is 1 plus 1, that gives us 2. Okay, yeah, that's right. So any balance here should be 2 units. And it is compounding quarterly, so you will use n equal to 4. So here we have 1 unit times 1 plus 100% 4 raised to 4 times 1. So then again, we're going to use Excel for this. Use Excel to get a number. It should be 1 times parentheses 1 plus 100% that's 4 raised to the 4th power. And that becomes $2.44. $2.44. So go back here. As you can see, the more compounding periods we have with approximately 4. So the result is 2.44. Okay, so now next thing is compounding monthly. So n equal to 12. So 1 times 1 plus 100%. 12 raised to 12 times 1. Let's see what that is. The formula here, got that, and let's get a result really quickly. So it's 1 plus 100% by 12 raised to the 12th power. As you can see, this is 2.61. 2.61. So this is equal to 2.61. And One more time, you see as compounding periods increases, the ending balance increases. This compounded daily, that would be 365. So this is 1 times 1 plus 100% by 365 to 365 times 1. Let's see what that is. So this is equal to 1 plus 100% by 365 raised to 365th power. And this turned out to be 2.71 unit, $2.71 if you want to put in a dollar amount. 2.71. Again, it proves the trend, right? As the number of compounding periods increases, ending balance increases. The last one is hourly, compounding hourly, so 365 days. Every day has 24 hours. 365 times 24 gives us 8,760. This is 1 plus 100% by 8,760 raised to 8,760 times 1. Let's see what that is. So this is 1 plus 100% by 8,760 and raised to 8,760 power. It's another bit 2.718. So this one I'm gonna need two more decimal, 2.718, because that's a number getting close to Euler number, which is natural number, 2.718. Again, as the number of compounding periods increases, ending balance increases. Okay. So now, as you can see, when this n approaches infinity here, this is infinity, the limit of this will approach Euler number, which is E, right? Natural number or Euler number. That's approximately equal to 2.718, 281828. You can pick a bigger number for n. Same thing. I'm going to show you one more, right? So let's say number of compounding periods, it's 100,000. So 1 plus 100% by 100,000 and raised to 100,000 power. As you can see, this number will get close to the Euler number. As the number of compounding periods increases, then the result will approach it Euler number, natural number. And that's how Euler developed this continuous compounding element we call the Euler number. Okay. Okay, so now limit when n approaches infinity for this 1 plus 1 over n raised to n power equal to e, which is approximately 2.718. This number e is a constant. It's like pi we learned in high school, referred to as the natural base. Logarithm with base e is also called a natural logarithm, Ln, right? So we have a logarithm function f of x equals to ln of x. Ln comes from this. Now let's take a look at how we come up with the exponential, the graph of exponential function, and then logarithm function with base e. First of all, we're picking some x values from -1, 0, 1, 2, 1, 2, right? And we plug into the exponential function e to the x. So first one is e raised to -1 power, approximately equal 0.37. Second one, e to the 0, we get 1. E to the 1, we get 2.72 approximately. e to the second we get 7.39. So and from there we'll be able to plot those 5 points, end up with this f of x equal to e to the x. Okay. And now since ln of x is the inverse function of exponential function, so that it's for the mirror image based on y equal to x. We call this identity function. So the algorithm function will look like this. So all these points for the mirror image down here. For mirror image based on y equal to x. Okay. And now we connect those 4 points, we get a natural logarithm function. F of x equal to ln of x. So this one is ln of x. And we actually talk about that in chapter 2, but just quick review how the graph look like. All right. Now, let's look at the continuous compounding formula. Okay. So A ending balance equal to principal times e to the RT. Right. And A is the value of the continuous compounding, meaning ending balance. Then I'll say that P is the principal value. I is annual interest rate, and T is time. All right, so as I mentioned earlier, I want to show you a real-world example on this. Okay, so let me just open the browser. All right, so if you go to Google and type in national debt, real time, and you're going to see the national debt, U.S. national debt clock. You look at that. Let's wait for a second. As you can see, this is U.S. national debt, and it's compounded continuously. So this is one of the important application of the continuous compounding formula. So national debt compounded continuously. As you can see, this number go up every second because it's compounded continuously. And if you're interested in this topic, you can dig deeper into this and see. All the countries have national debt. They all behave in a similar way. So example number 1, $1,000 is deposited into account, yielding 5% continuously. How much will be in the account for 10 years? So right here we have the formula, continuous compounding formula. 1,000 here is the initial value, which is $1,000. The rate is 5%. Okay, and time t equal to 10. So this formula, there are 4 variables. We know 3 out of 4 variables. Then we'll be able to solve for the unknown. So the unknown here is ending balance, principal times e to the RT. Okay. Principal is $1,000 times E. R, that's 5%. Now one more time, I use a calculator Excel to show you quickly the result. So just put into the Excel. So 1,000 times EXP, open parentheses, 5% times 10 years. Okay, and that should give us a result. Let's see what it is. Okay, so result is $1,648 and then 72 cents. Okay, 1648.72. So the ending balance is $1,648 and 72 cents. So this is the ending balance after 10 years. Based on the current condition, compounding continuously. And then continuous compounding is the best compounding methods in the marketplace. Now, example 2, how much should we deposit in an account yielding 4.38% compounding continuously, so that we will have $100,000 in 10 years and 10 months. Now again, we're using the same formula, but we are given some information here. First of all, is interest rate is 4.38%. Turning through a decimal is 4.375%. We know the time t is 10 years, 10 months. And again, time t must be in years, so it's 10 and then 10 over 12. Simplify is 10 and 12 over 6. Now we're going to turn into a improper fraction. 10 times 6 gives us 60, adding 5, 65 over 6 years. And then we also know the ending 100,000 years ending balance, A equal to 100,000. So we want to know the principal amount. How much do we need to invest as a principal right now? So we look for P. So write the formula A equal to P times E star T. Okay. Now replace A with 100,000. Looking for P times E. The rate is 4.375% times time T, that's 65 over 6. Okay. And now we want to solve for P, so we have to divide both sides of the equation by E 4.375% times 65 over 6. Okay, from both sides of the equation. And cancel the E, so now the principal P is by itself. That's what we're looking for. P equals 100,000 over and E 4.375% is 0.0435 multiplied by 65 over 6. And let's see what that is. Again, Excel is needed. Let me show you how to get that. So that's 100,000 by EXP. If you want to put in 4.375%, no problem. And multiply by 65 over 6. And that should give us a result, right? Once you input properly. So this $62,253.32. 253.32. So we get a 62,000. $253.32. $253.32. And this is the initial deposit or initial investment needed in the account to achieve the goal in 10 years and then 10 months. Okay, and then example 3, how long will it take $9,000 to grow to $15,000 at a 418% compounded continuously? So now here we're looking for how long, meaning looking for time t. Sure, so time t is and we know $9,000 is principal, initial investment. Ending balance A is 15,000. Okay, and rate is 4.18%. 4.18% is 4.125%. The decimal number will be 0.04125. Okay. So and the only thing we don't know is time t. So we're gonna solve for it. So A equal to principal times E raised to RT. We solve for time t. Ending balance 15,000. So 9,000. E rate is 0.04125 times t. So step 1, we isolate the variable term by dividing 9,000 from both sides of the equation. And we simplify, right? Drop the zeros in the back. 15 and I both will reduce by 3, so end up with 5 over 3 equal to E 0.4125. Let's reverse the order here. We got E 0.04125 T 5 over 3. Now in order to get T by itself, we need to take Ln from both sides of the equation. E 0.4125 Ln of 5 over 3. Let's simplify this, we get 0.04125 T equal to Ln of. And from there, dividing the decimal number 0.04125. Okay, cancel that and times itself. Let's see what happens. Let's go to the Excel note. This is equal to ln of 5 over 3 by 4.125%. If you want to do percentage, no problem. Get that. So it's 12.4 years. Approximately takes about 12.4 years to achieve the goal. So the answer here is 12.4 years. All right, that's example 3. Example 4. At what interest rate compounding continuously $7,500 go to $12,000 in 7 years and 7 months? For interest rate for R here. We know the initial balance, the initial deposit is $7,500, and then the ending balance rate is $12,000, and time T is 7 years and 7 months, 7 and 7 for 12. And again, we do an improper fraction. 7 times 12 is 84, and 7 is 91 over 12. Then let's apply the formula ending balance equal to principal times e to the RT. Throwing A $12,000 and P is 7,500. R times 91 over 12. And first step was dividing 7,500 on both sides of the equation. Cancel that. And we drop a couple zeros on the left. So we get 120 by 75. 120 over 75 on the left. And reverse these two. 91 over 12 times R. It'll be slightly easier to follow that switching order. Now reverse order. So it means E is 91 over 12 times R. That's equal to 120 over 75. Now we're taking Ln one more time to offset the exponential function base E. Okay, Ln and E, they offset each other. Ln of E to the x becomes x because natural exponential function and natural logarithm function, they are inverse function, so they offset each other without x. So similarly here, like 12 times R equal Ln of 120 over 75. Now we need to get rid of the fraction in front of the R, so multiply by reciprocal 12 over 91. 12 over 91. Okay. So this whole thing gets cancelled. R is by itself. R is approximately equal to Ln of 120 over 75 times 12 over 91. Let's see what that is. Ln of 120 by 75 and multiply by 12 over 91. Okay. And that should do it. We should get a result right here. So this turned out to be 4 decimal place, 0.0620, 0.0620, 0.0620. So if you turn in percentage, it will be 6.20%. Okay, so that's a interest rate we're looking for. Now, next topic is about effective interest rate, or APR. Effective interest rate is also called APR. For credit card, like financial instrument, they use APR, effective interest rate. They also have another term called nominal interest rate. And nominal interest rate is basically interest rate at a face value. So nominal interest rate is interest rate quoted based on the period. It means compounded yearly. That's why it's annual interest rate. Also another word for the nominal interest rate is annual interest rate. And an effective interest rate is the actual interest earned or paid in a given year, taking into the consideration of the compounding period. So for a lot of financial instruments like credit card, it's compounding monthly, so meaning it's actual interest rate compounded monthly. And let's take into consideration of this example, 18% compounding monthly, 18%, that's what we call the face value. So this is a nominal interest rate. So 18% is a nominal interest rate. Now, since it's compounding monthly, then we can, based on this, get an actual annual percentage rate of APR, right, according to the nominal interest rate. Because we have a different compounding period, the 18% is compounding yearly. So right here, it's, we try to figure out the annual percentage rate based on the compounding period monthly. So what this really means is interest rate per month is, if you look at that, it's 18% by 12, which is 1.5%. Number of interest period per year is equal to 12. Now, bank will charge 1.5% interest each month on your unpaid balance. If you borrow money, you will earn 1.5% interest each month on your remaining balance if you deposit money. But remember, since it's compounded monthly, then a newly earned interest will generate more interest. So that's why this compounding periods matters. Now, in order to get the effective interest rate, or APR, based on this 18% nominal interest rate, we need to use this formula for effective annual interest rate. You can say APR. Okay, I'm using I with the lowercase e represent the effective annual interest rate, which is equal to open parenthesis 1 plus annual interest rate R, which is nominal interest rate per year over number of compounding periods per year raised to n power minus 1. So effective interest rate I with the subscript E is the same thing as APR. So if you want to write APR formula, it will be exactly the same. Because these two terms are the same, power n to n power minus 1. Now here R represents the nominal rate. Now, suppose you invest $1 1 year at 18% compounding monthly, how much interest would you earn? So we can do this. So APR, we can just directly solve APR. So it's going to be 1 plus R of n to n power minus 1. So this is going to be 1 plus 18% over 12. Number compounding period is 12 by 18%, nominal rate 18%. Yeah, so there's 12 power minus 1. And then let's see what that is. Let's put into the Excel. equal to 1 plus 18% 12 raised to 12 power minus 1. So this is turned out to be, if you turn into 4 decimal place, is 0.1956. This means is the actual borrowing cost, or the effective interest rate, or APR, it's 0.1956. So this 18% is not a accurate description of the actual borrowing cost. So actually, this should be 0.1956, and then this turned out to be approximately 19.56%. By combining monthly, the effective interest rate becomes 19.56%. So 19.56% compounded monthly. And let's look at a couple of practice problems. If your credit card calculates interest based on 12.5% nominal interest rate, the given R here. What is your monthly interest rate and an annual effective interest rate respectively? So monthly interest rate are equal to R over N, so 12.5% over 12. And that's approximately, run it to, let me see. Let's see what that is. Approximately here. We get 12.5% by 12. So this is going to be 1.04%. Run it 4 decimal place. 1.04%. Approximately. And this is monthly interest. Now the APR, effective interest rate, APR equal to 1 plus R over N power minus 1. Now it should be 1 plus 12.5% by 12 is per power minus 1. Let's see what that is. What time we put into the Excel get a result. And this turned out to be 0.142, 1324. If you run into 4 decimal places, 1324. And this is about 13.24%. Okay, so this is actual APR, or the effective interest rate. And more practice. Determine the effective interest rate on account paying 4.75% compounded weekly. So for A here, R is 4.78%. Compounding period is equal to 52 weeks in a given year. So we solve for the APR. So APR here equal to 1 plus R over N to N power minus 1. So this is 1 plus 4.78% by 52 raised to 52nd power minus 1. Let's see what that is. And again, the effective interest rate usually it's always higher than the nominal interest rate because of the compounding effect. So right here should be yes, 1 plus 4.78%, 4.78%, divided by 52 raised to 52nd power minus 1. And this will turn out to be, we run it to 4 decimal place. And again, it's conventional to run it to 4 decimal place 0.0489. So the result is 0.0489, and that's approximately 4.89%. Effective interest rate, again, compared to 4.78%, is higher. And second one, determine the effective interest rate of an account paying 4.78% compounded daily. It's the same 4.78%. And number compounding period is 360 daily, so 365 days in a given year. So APR, or effective interest rate, equal to 1 plus I over N, 1 power minus 1. So this is 1 plus 4.78% over 365 raised to 365 power minus 1. Let's see what that is. One plus 4.78% over 365 raised to 365 power. Point slightly higher. 0.0490. So the more compounding period does give us a higher interest rate. So it's 4.90%. And okay, so this is compounded daily, right? So APR for compounded daily, same interest rate. And this table summarizes, the relationship between the nominal interest rate and then effective interest rate, APR. As you can see, when the compounding period increases, then the rate increases, right? You look at each one of these, follow the same pattern. All right. Different rate, when the compounding period increases, then the APR becomes higher, the rate becomes higher. That's how this thing goes. Okay, and then I think I'll stop here. We'll finish the other half another lecture video.